Hi, I'm Cassidy Chellis, and my final year project was to develop a simple water market model. In this presentation, I'm looking to show you the fruits of a year of labor and my hopes for the future of this ongoing project. So originally the goal of this project was simply to create a condensed model of a water market, which could allow for realistic trading statistics, streamflow output, and irrigation statistics. The project evolved, however, and the current goal has been broadened with the aim of developing a baseline model upon which we can continually add features and get closer and closer to a truly accurate model of a river economy, specifically an accurate model of the Murray River economy, taking into account its special intricacies. For the vast majority of water market models, there need to be two separate models working in conjunction. First is a hydrological model. This model needs to take inputs of irrigation and rainfall and ultimately result in some measurable physical state. So this can be soil moisture content, as it is in this project, but it can also be things such as soil runoff or even crop yields. The second model needs to take the physical system and model the way actors are going to react to it. So this can be stochastic, or it can even focus on average effect. However, in this model, we have chosen to use a set of stochastic agents acting in an auction environment. And what we're seeing here is the result of our hydrological model following calibration. So this has the input of rainfall and an output of runoff. And despite this, what we actually care about is the soil moisture content. However, we can use rainfall runoff data to calibrate accurate soil moisture model, which is indeed what we've done. As you can see, rainfall doesn't necessarily correlate strongly with runoff. However, we have been able to successfully predict runoff with rainfall as the sole input. Due to the time step used being too coarse, we were unable to get a more jagged result. However, this didn't end up affecting the accuracy of our end results. What you're seeing here is the completed economic model. It's a discriminatory price double auction. So irrigators can observe their soil, they can predict how much water they're going to need based on their rainfall estimates, and then they can trade their water allotments accordingly. As many actors are going to walk away empty-handed due to poor bidding strategies, we have actually implemented a behavioral update system in which they can change their bidding strategies over time. And finally, we have an example of the model in action. Irrigators want to maintain a certain water deficit in the soil. Too high, and the crop yield plummets. Too low, and they're wasting money on water that they could have sold. So here, we're seeing actors learning and bidding so that they can maintain constant water deficits, interrupted only by periods of rainfall. So why did I, an electrical and computer systems engineering student, take on a project like this? You know, when I saw this project, I thought to myself, utility markets, thousands of buyers and sellers trading utility. What I learned from this project could be applied to any utility market, especially electricity. I'm not sure that a huge amount of what I learned is all that applicable to energy, but I don't regret my choice for a second because I did indeed learn so much. So let's get into the detailed design decisions that I used to get this model working. First off, I needed to decide between stochastics or average effects. My housemate is an economics major. I've talked to him enough to know I wasn't going to be able to learn enough economics in a year to actually contribute to the field. Instead, I needed to make agents who could act rationally, a principle I somewhat understand. These agents would need to make their own financial decisions, irrigation decisions, and of course, monitor their own patches of land. Now, there are a lot of hydrological models out there. Not many of them are simple. One can use proprietary programs like FlowLogo, that's in the bottom left, or one can use more analytical mathematical models such as the water balance model in the top left, or one based on probability density functions applied to water percolation. However, in addition to being extremely difficult to model, many of these models required a great deal of specificity about the types of land we're working on. I needed generality. Luckily, my supervisor had already worked with a very simple model, which I knew and he knew was well within my reach as an undergrad. So the rainfall runoff model. It has a lot of equations involved, but luckily for me, they are all well defined and reasonably simple to implement. There are 3 soil reservoirs, being topsoil moisture, groundwater, and also deep storage. Rainfall and irrigation enter, and they're partitioned between topsoil and groundwater. Water evaporates, water percolates, and ultimately it flows out of the soil. But there are a lot of parameters. 11 of them. To optimize the 11 parameters, I just took a random walk in 11-dimensional space. which sounds hideously inefficient because it is, but it worked. I changed parameters at random, and if it resulted in a better result, I kept it. I repeated this a few thousand times overnight, and I ended up getting some really good results and some really good parameters. In my report, I've actually included a full justification for why randomized gradient descent works the way it does. But until then, rest assured that it really does, and I can show you proper results of that later. Now, luckily, the problem of economic models was already decided for me. Water's traded using a discriminatory price double auction system, and I'll explain that very soon. But actors have a set amount of water that they're allowed to use over the course of a year. If at some point they think they're going to use a different amount of water, then they can buy and sell their entitlements at an auction. Of course, some actors won't be lucky at an auction, and these actors need a way to learn so that the market can continue to evolve and react to external shocks. So in a discriminatory price double auction, bids to buy water are sorted from highest to lowest, and bids to sell are sorted in reverse order, so that's lowest to highest. That's price. The highest buying price is matched with the lowest selling price, and the trades carried out at the mean of the two prices. And these two bids are then removed from the pool. Once the two bids at the top of the pool are incompatible, i.e. the buyer is asking for a lower price than the seller is offering, the auction's completed and everyone walks away empty-handed. So agents want to run out of water at the end of the year. That's it. They haven't wasted money on water allocations. They do this by trying to buy, sell, and irrigate so that they can stay on a smooth trajectory to optimal water purchases. After checking the moisture content of their soil, they predict how much they're going to need to irrigate, they place bids on the market for whatever water they need to move, and then the auction system begins. If the agent walks away without a successful trade, then they change their rent-seeking behavior to move toward the market target price. Finally, they irrigate their soil, and they wait to observe soil moisture again, and that's where we go back into the hydrological model. So let's take a closer look at our hydrological results. Yes, model runoff does fluctuate with the actual runoff, but it fails to capture the peaks and troughs, and keep in mind this is a log scale graph. And this can be explained by the simple fact that the model updates daily rather than per second, say. The same amount of rain over an hour or a day may lead to, say, increased soil moisture, or it may lead to flash flooding. Due to the data available being on a daily grain, this is sufficiently accurate, although modeling flash flooding is something we'd like to do later on. And finally, this is the culmination of a year's work. This relatively unimpressive graph, what we see at least, is irrigators doing exactly as they should. So the graph shows soil moisture deficit over time. Different actors are comfortable with different deficits according to behavioral parameters, and they're going to buy and sell and irrigate to ensure that they stay at their exact desired deficit. And that's what we're seeing here. When the curves flatten, that is actually the actors buying and selling to ensure that they are at the perfect level of water deficit. So I want to model the Murray with this model, and it's a very long way away, but I can summarize the key steps here. 6 features, and we will have a Murray-Darling Basin model of unparalleled accuracy. Until then, I'm very happy to say that this project has been a success, and I cannot thank my supervisors enough. That's Associate Professor Valentine Powles, Dr. Stuart Walsh, and Dr. Ashkan Shokri. Thank you very much for your attention, and I'm very excited to see the other final year projects.